Welcome to the Explainer. So, when you look at a medical x-ray, have you ever actually stopped and wondered how that incredibly crisp, detailed image of your bones was captured? Because it's definitely not just a simple flash of light. Hiding inside that heavy equipment is literally a whole universe of extreme, high-speed physics and just unbelievable mechanical engineering. Today, we're going to absolutely demystify exactly what happens inside an x-ray machine. And to make sure we're grounded in pure clinical facts, today's insights are drawn straight out of the core BMRIT curriculum source material. We're skipping right past those basic superficial summaries to really explore the exact internal engineering and the sophisticated physics that BMRIT students actually learn to master this life-saving tech. Okay, let's dive into this. Here is our roadmap: anatomy of the machine, inside the vacuum tube, managing the heat problem, the line focus principle, the anode heel effect, and finally, our key takeaways. All right, Section 1, anatomy of the machine. I want you to imagine we're conceptually building an X-ray machine from scratch, starting right at the wall socket. Trace this electrical journey with me, okay? Standard means power enters the machine and hits the autotransformer first. That's where the operator selects the precise tube voltage. Next up, that power travels over to the high-voltage transformer. This is a step-up transformer, so it takes that everyday electrical input and literally supercharges it up to the tens or even hundreds of kilovolts we need. From there, the power runs through rectifiers. Now, these are crucial because they brilliantly convert the alternating current, the AC, into direct current, DC. This is non-negotiable because the X-ray tube absolutely needs electrons flowing in one single direction. And finally, all this highly refined power reaches the X-ray tube itself to generate the actual X-rays. But hey, before that electricity even makes it to the tube, it's got to be managed. That's exactly where the control console comes into play. Think of this as the brain of the whole operation. This is where the technologist precisely dials in the kilovoltage peak, the milliamperage, and the exact exposure time, safely orchestrating the entire sequence before it even starts. Moving right along to Section 2, inside the vacuum tube. Getting inside the tube brings up a really fascinating question. Why must the X-ray tube be a completely evacuated vacuum envelope? The tube isn't just some protective casing. It's historically made of glass, increasingly metal or glass these days, but it is completely empty of air. It's not just a feature, it's a brilliant engineering fix to a major physics headache. Because think about it, if there were any residual gas inside that tube, our electrons, which are traveling at just phenomenal speeds, would crash right into those gas molecules. It'd be like driving a race car through a bumper car arena. This would scatter the electrons, drain away their kinetic energy, and honestly just produce a bunch of unwanted, useless radiation. So the vacuum guarantees a perfectly clear, unobstructed path. And this brilliantly illustrates our two main stars sitting right inside that vacuum. On the left, we've got the negative cathode, which shapes the electron cloud. It's got a tungsten filament and a molybdenum focusing cup. Then, over on the right, you have the positive anode, acting as our high-heat target, built tough out of tungsten to handle the intense physics coming its way. So, how do we actually get the electrons to travel between them? 2 words: thermionic emission. When an electrical current heats up that tiny tungsten filament on the cathode, well, think of it kind of like a toaster on maximum power. It literally boils electrons right off the hot metal surface. They're liberated and primed to be violently accelerated straight across the vacuum toward that positive anode. Okay, Section 3, managing the heat problem. Now, this violent collision of electrons comes with a massively dangerous byproduct. Get this, 99%. When those high-speed electrons slam into the anode target, over 99% of their kinetic energy is instantly converted into pure destructive heat. Literally less than 1% actually becomes the useful X-rays we want. With that unbelievable amount of heat, a stationary target would just melt into a puddle almost instantly. So how on earth did engineers solve this? The rotating anode. Instead of a fixed target, the tungsten target is a disk that spins continuously during the exposure. And we're not talking a lazy spin. It rotates at terrifying speeds, anywhere from 3,000 to 10,000 RPM. That is roughly the idle speed of a commercial jet engine. This violently fast spinning spreads that blistering heat all the way around the edge of the disk. And what's really wild? It's driven by an induction motor sitting completely outside the tube. That means no mechanical shaft ever has to physically pierce the glass and ruin that precious vacuum. Which brings us to Section 4, the line focus principle. Solving that heat problem actually creates this really tricky paradox for image quality. Here is the geometric challenge. To get a perfectly sharp medical image with zero blur, we need our X-rays to originate from the absolute smallest possible point, right? A tiny focal spot. But, as we literally just saw, if the electron beam hits a tiny spot, the heat is too concentrated and our metal target melts. So, how do we get a tiny spot for sharpness, but a huge area to dissipate the heat? Now, what's really interesting about this slide is the solution itself. It's basically an optical illusion. By simply angling the target face, usually somewhere between 6 and 17 degrees, the actual physical area taking the hit and absorbing the heat is quite large. It acts like a massive heat sink. But because of the angle, when it projects downward toward the patient, it geometrically appears as a tiny, highly concentrated point for maximum sharpness. It's an absolute engineering marvel that makes modern diagnostic imaging completely possible.
All right, Section 5, the anode heel effect.
So that cleverly angled target, it actually has a weird little quirk. The X-ray beam shooting out of the tube is not totally uniform in its strength. The X-rays that are produced deep within the target on the anode side have to actually push their way through more of that solid tungsten metal just to escape the tube. Because they get attenuated or weakened by the target itself, the anode side of the resulting beam has a noticeably lower intensity. Conversely, the beam coming off the cathode side is significantly stronger. So what does this all mean for a patient? Well, this is how technologists use that physics quirk to their advantage in the clinic. Let's say a patient is getting an X-ray of a body part with varying thickness, like the femur, right? It's incredibly thick up at the hip, but way thinner down by the knee. The technologist will purposely position the thicker end of the patient toward the stronger cathode side of the tube. That higher beam intensity naturally compensates for the thicker bone, giving you a perfectly uniform diagnostic image. Just brilliant. And finally, Section 6, Key Takeaways. Let's rapidly distill this incredible journey into our core takeaways. First, X-ray tubes absolutely require a complete vacuum. Otherwise, gas molecules would just scatter the electrons everywhere. Second, thermionic emission is that toaster-like process that literally boils electrons right off the cathode filament. Third, we manage the insane reality that 99% of the energy turns into heat by using those extremely fast rotating anodes. Fourth, the line focus principle brilliantly balances our need for image sharpness with heat dissipation just by angling the target. And finally, the heel effect reminds us that the beam isn't totally uniform, which requires positioning thicker anatomy on the stronger cathode side. We all kind of take medical imaging for granted, right? Seeing it as just a quick, simple snapshot at the doctor's office. But next time you look at a medical X-ray, will you recognize all the invisible, high-speed, high-heat universe operating inside that machine? Honestly, every single pixel of that image is a testament to extraordinary physics and brilliant engineering. Thank you so much for joining me on this explainer. Keep feeding your curiosity, and I will see you next time.